Welcome to the Platform Engineering Playbook podcast, where everything you hear is built, reviewed, and improved by AI, by me, and by you, the listener. This show keeps me, and hopefully you, up to speed on the latest in platform engineering, SRE, DevOps, and production engineering. It's a living experiment in how AI can help us track, explain, and discuss the fast-moving world of infrastructure. Every episode is open source. If you've got something to add, correct, or challenge, head to platform-engineering-playbook.com. You'll find all the content and a link to the GitHub repo. Open a pull request, join the conversation, and make the playbook smarter. Let's get into it.
Let's connect to what we've built. Pause and try to remember. In Episode 3, how does Aurora replicate data between regions? And in Episode 4, how do independent EKS clusters coordinate? Take a second. Aurora storage layer ships redo logs across regions. That 45 to 85 millisecond lag? Part of that is network latency. EKS, independent clusters, coordinate at infrastructure level, Aurora for data, DNS for traffic, CI/CD for deployments. But here's what we haven't answered. How do they communicate? What network paths do Aurora redo logs actually take? When your front-end pod in US East 1 calls an API in US West 2, what happens at the network layer? Today, you're learning the network foundation. This is what everything else runs on. Get this wrong, and your entire multi-region architecture breaks. Get it right, and it's invisible. By the end of this lesson, you'll know exactly how to connect your multi-region infrastructure without creating hidden bottlenecks or burning cash on unexpected data transfer charges. What you'll master today: when to use Transit Gateway versus VPC peering, and why Transit Gateway scales beyond 100 VPC connections. How to design network topology that doesn't explode your route tables. PrivateLink for secure cross-region service access without exposing traffic to the internet. And the network layer mistakes that cost $50,000 monthly in surprise data transfer bills. Let's start with the problem nobody explains clearly enough. You've got Aurora in US East 1 and US West 2. You've got EKS clusters in both regions. They're running in separate VPCs. How do they talk? They can't. Not yet. VPCs are isolated by default. Your Aurora primary in the US East 1 VPC can't send redo logs to Aurora secondary in the US West 2 VPC. Your EKS pod in one region can't reach services in another region. Your monitoring system in one VPC can't scrape metrics from another VPC. You have three options. 1. Public internet. Terrible idea. Security nightmare. High latency. Unpredictable performance. 2. VPC peering. Direct connection between two VPCs. 3. Transit Gateway. Hub and spoke model. Connecting many VPCs. 4. Or PrivateLink. Private service endpoints. The choice determines your scalability, cost, and operational complexity. And most teams get this wrong initially. Here's a real example. E-commerce company built hot warm with VPC peering. Started simple. 4 VPCs. Primary and secondary in 2 regions. 2 peering connections. Easy to manage. 2 years later? 40 VPCs. Different business units. Multiple services. Separate environments for staging, testing, security scanning. The architecture evolved. The network design didn't. VPC peering requires n times n minus 1 divided by 2 connections. 40 VPCs equals 780 peering connections. That's not a typo. 780 separate peering connections to manage. Each peering connection adds routes to your route tables. And here's the limit that broke them. VPCs have a 125 route table entry limit. Hard limit. You hit it, traffic stops routing. Services fail. Your multi-region architecture goes down. They hit the limit during a normal deployment. Added one more VPC. Route tables maxed out. Production broke. 4-hour outage. $200,000 revenue loss. Transit Gateway would have cost $300 per month. The outage cost $200,000. The math isn't even close. Let's break down why VPC peering looks simple but doesn't scale. VPC peering is a direct network connection between two VPCs, point to point. Your US East 1 VPC connects to your US West 2 VPC. Traffic flows directly between them. Private IPs work. No internet gateway needed. For small deployments, it's perfect. Same region or cross-region, doesn't matter. Traffic never touches public internet. Latency is low, about 15 milliseconds cross-region for US East 1 to US West 2. Cost is straightforward. Just data transfer at 2 cents per gigabyte. The setup is dead simple. A WS console. A few clicks. Done. No additional per hour costs. For 2 to 4 VPCs, this is the right choice. But watch what happens as you grow. DAS, 2 VPCs, 1 peering connection. Easy. 4 VPCs, 6 peering connections. Still manageable. 10 VPCs, 45 peering connections. Starting to get messy. 20 VPCs, 190 peering connections. Good luck managing that. 40 VPCs, 780 peering connections. This is where production breaks. The formula is n times n minus 1 divided by 2, where n is your VPC count. It's quadratic growth, and it kills you fast. Each peering connection adds routes to your route tables. The VPC route table limit is 125 entries. You add routes for each peered VPC, plus your local routes. Internet gateway, NAT gateway. You run out of space. When you hit that limit, new routes fail. Traffic that should route to peered VPCs doesn't. Services can't communicate. Your applications break. And the error messages don't make it obvious. They just time out or fail to connect. Now let's talk about costs, because they're not insignificant. Data transfer across regions costs 2 cents per gigabyte. If Aurora replicates 100 gigabytes per day, that's $2 per day, $60 per month. Not terrible. But if you're replicating a terabyte per day, $20 per day, $600 per month. Just for Aurora replication. Add in your application traffic monitoring data, log shipping, backup replication. This adds up fast. When do you use VPC peering? Small deployments with 4 or fewer VPCs. Simple architectures. Primary and secondary regions, minimal services. When you're cost sensitive and can't justify per hour charges. And critically, when you know your VPC count won't grow significantly. If there's any chance you'll add VPCs as you grow. New business units, more services, additional environments. Don't start with VPC peering. You'll migrate to Transit Gateway later, and migrations are painful. Now let's talk about Transit Gateway, because this is what actually scales. Think of it like an airport hub. Instead of direct flights between every city, that's VPC peering, you route through a central hub. All cities connect to the hub. The hub routes traffic between them. Transit Gateway is that hub. All VPCs connect to Transit Gateway. Transit Gateway routes traffic between them. Here's the scaling difference. N VPCs equals N connections, not N squared. 40 VPCs, 40 connections. 100 VPCs, 100 connections. Linear scaling, no route table explosion. Here's how it works in practice. You create a transit gateway in each region. You attach VPCs to the transit gateway. The transit gateway handles routing between VPCs automatically. You can peer transit gateways across regions, and you get centralized control of all your routing. Picture your US East 1 architecture. Transit Gateway connects your production VPC, staging VPC, monitoring VPC, and data VPC. Same structure in US West 2. Then you create a Transit Gateway peering connection between regions. Cross-region traffic flows, VPC to Transit Gateway peering to the other region's Transit Gateway, then to the destination VPC. 2 hops through Transit Gateways, but the routing is automatic. Advantages are significant. Scales linearly, N connections, not N squared. Centralized routing control. One place to manage all routes. No route table limit issues. Transit Gateway handles routing internally. Supports transitive routing. VPCA can reach VPCC through VPCB, and it integrates with VPNs and Direct Connect. But it's not free. Transit Gateway costs 5 cents per hour per attachment. That's $36 per month per VPC attached. 10 VPCs attached equals $360 per month base cost, plus data transfer at 2 cents per gigabyte, same as VPC peering. Compare to VPC peering, $0 per hour base cost, just data transfer. So where's the crossover point? If you have more than 3 to 4 VPCs, Transit Gateway operational simplicity justifies the cost. You're paying for sanity. For not dealing with quadratic connection growth. For not hitting route table limits at 2 a.m. Performance is solid, bandwidth up to 50 gigabits per VPC attachment. That's enough for most workloads. Latency adds 1 to 2 milliseconds compared to VPC peering. For almost all use cases, that's negligible. And you get burst capacity over 100 gigabits aggregate across all attachments. When do you use Transit Gateway? More than 4 to 5 VPCs. Growth expected. You're adding business units, services, environments. You need centralized routing control, multi-region architecture with many services. Or you need transitive routing. Let me show you a real production example. SaaS company running hot-warm architecture. US East 1 has 12 VPCs. Production, staging, per-service VPCs for microservices, monitoring, security scanning, data processing. US West 2 mirrors that architecture. 12 VPCs in each region. They use Transit Gateway in each region, Transit Gateway peering between regions, 24 total attachments across both regions. Cost breakdown. 24 attachments times $36 equals $864 per month base. Data transfer. 500 gigabytes per day times 2 cents times 30 days equals $300 per month. Total, $1,164 monthly. What would VPC peering cost? 12 VPCs in each region equals 24 VPCs total. That's 276 peering connections to manage. The route table management is a nightmare. They had 3 production outages in 6 months from routing misconfigurations before migrating to Transit Gateway. They paid the $864 per month for operational sanity. It was absolutely worth it. No more 2 a.m. pages from routing failures. No more manual route table updates. No more hitting limits. Now let's talk about PrivateLink, because it solves a different problem entirely. PrivateLink lets you expose services privately without VPC peering or Transit Gateway. The service provider creates a VPC endpoint service. The service consumer creates a VPC endpoint. Traffic stays on the AWS backbone, never touches public internet. And critically, no VPC-CIDR overlap issues. Here's how it works. Service provider in US East 1. You run your service behind a network load balancer. You create a VPC endpoint service pointing to that NLB. You share the endpoint service name with consumers. Service consumer in US West 2. They create a VPC endpoint in their VPC. They point it to your endpoint service name. They access your service via private DNS or IP. Traffic flows from consumer VPC through PrivateLink to your VPC. Secure, private, no internet exposure. Use cases are specific. Expose APIs or services to other VPCs or regions without full VPC connectivity. Third-party integrations. Share services with partner VPCs without giving them access to your entire network. Compliance requirements where you cannot expose traffic to the internet. Or SaaS service delivery. Your product accessed by customer VPCs. Advantages are compelling for service-oriented architectures. No CIDR overlap issues. Each consumer gets a unique elastic network interface. Scales to thousands of consumers. Security isolation. Consumers can't see each other. No route table management. Cross-region supported. Limitations matter though. Requires network load balancer at 2 cents per hour, about $16 per month. PrivateLink endpoint costs 1 cent per hour, $7 per month per consumer. Data transfer is 1 cent per gigabyte, cheaper than transit gateway or peering across regions. But only TCP traffic works. No UDP, no ICMP. Cost example. Monitoring service accessed by 20 VPCs across regions. Network load balancer, $16 per month. 20 endpoints times $7 equals $140 per month. Data transfer, 50 gigabytes per day times 1 cent times 30 days equals $15 per month. Total, $171 monthly. Alternative with VPC peering. 20 peering connections, routing complexity, no isolation between consumers. Alternative with transit gateway. 20 attachments times $36 equals $720 per month. For service-oriented architectures, PrivateLink wins on cost and operational simplicity. Let me give you some design principles that actually matter in production. First, start simple. Use VPC peering for your initial hot-warm setup. Primary plus secondary equals 2 VPCs per region equals 4 total. That's manageable. Add transit gateway when you hit 5 VPCs or foresee growth. Don't over-engineer early. Second, plan for data transfer costs. Cross-region bandwidth isn't free. 2 cents per gigabyte adds up fast. 1 terabyte per month is $20. 10 terabytes is $200. 100 terabytes is $2,000. 1 petabyte is $20,000. If Aurora replicates heavily or your EKS services are chatty across regions, this hits your budget hard. Designed to minimize cross-region traffic. Keep traffic local when possible. Remember Episode 4's service mesh and external DNS? They prefer local endpoints. Cross-region is failover only. Third, avoid routing table explosion. The VPC route table limit is 125 entries. With VPC peering, you need routes to every peered VPC. 40 peered VPCs equals 40 routes plus local, internet gateway, NAT gateway. You're approaching the limit. Transit gateway needs 1 route to the transit gateway. It scales infinitely. Let's talk about the mistakes that kill multi-region projects, because I've seen these repeatedly. Mistake 1. Using the public internet for cross-region traffic. What? Engineers wrote cross-region traffic via public IPs to save money. Why it fails? Security exposure, high latency, unpredictable routing, and compliance violations. Fix. Always use VPC peering, transit gateway, or PrivateLink. The cost savings aren't worth the risk. Mistake 2. Ignoring data transfer costs. What? Architect the network without calculating cross-region bandwidth. Reality? $50,000 per month surprise bills for high-traffic architectures. I've seen this happen. A company didn't calculate Aurora replication plus application traffic plus monitoring and was hit with a $45,000 AWS bill at month end. The CFO was furious. Fix. Estimate traffic volumes up front, calculate costs, and design to minimize unnecessary cross-region transfers. Mistake 3. Hitting route table limits in production. What? Using VPC peering for 20 plus VPCs. Why it fails? You hit the 125 entry route table limit. Routes stop working. Services fail. Fix. Move to transit gateway before you hit 10 VPCs. Plan for growth. The migration path from peering to transit gateway is painful. Don't wait until you're forced to do it during an outage. Mistake 4. No bandwidth planning. What? Assume infinite cross-region bandwidth. Reality. Transit gateway is limited to 50 gigabps per attachment. If you're pushing high-volume data replication or real-time video processing, you can hit this. Fix. Calculate bandwidth needs, especially for burst traffic. Plan for peak, not average. Before we wrap up, pause and answer these questions. Question 1. You have 8 VPCs across 2 regions. Do you use VPC peering or transit gateway? Why? Question 2. What's the formula for calculating VPC peering connections? Question 3. Your Aurora replicates 500 gigabytes per day cross-region. What's the monthly data transfer cost? Take a moment. Answers. Question 1. Transit gateway. 8 VPCs is approaching the complexity threshold where VPC peering becomes unmanageable. If you expect any growth, and you probably do, transit gateway scales linearly. The cost is 8 times 36, which equals $288 per month base. Worth it for operational simplicity and avoiding future route table nightmares. Question 2. N times n-1 divided by 2, where n is the number of VPCs. 8 VPCs equals 8 times 7 divided by 2, which equals 28 peering connections. That's already complex to manage. It gets exponentially worse as you add VPCs. Question 3. 500 gigabytes per day times 30 days equals 15 terabytes per month. At 2 cents per gigabyte, that's $300 per month. Just for Aurora replication. This is why you design to minimize cross-region traffic when possible. Every gigabyte costs you. Let's recap what we covered. First, VPC peering is simple and low cost, but doesn't scale. Use it for 4 or fewer VPCs. The growth pattern is quadratic. Route table limits will break you. Second, transit gateway is a hub and spoke that scales linearly. Use it for 5+ VPCs or expected growth. It costs $36 per month per VPC attachment. Worth it for sanity and avoiding operational nightmares. Third, PrivateLink is for service-oriented architecture. You can expose APIs privately without full VPC connectivity. It's good for multi-consumer services and cheaper than transit gateway for service endpoints. Fourth, data transfer costs are 2 cents per gigabyte cross-region. Calculate before you build. 1 terabyte per month is $20. 100 terabytes per month is $2,000. This adds up fast at scale. Fifth, route table limits are 125 entries per VPC. VPC peering hits this with large deployments. Transit gateway scales infinitely because routing is handled centrally. Remember episode 2, the hot warm pattern with a 5-minute RTO? The network layer supports that. Aurora replication from episode 3 travels over these networks. EKS cross-cluster communication from episode 4 depends on this foundation. DNS failover needs network connectivity to reach services. Together, data layer, compute layer, network layer, that equals your complete multi-region architecture. We'll revisit Transit Gateway in episode 8 when we cover DNS and traffic management, how Route 53 integrates with your network topology. In episode 9, Cost Management, we'll optimize these network costs. And in episode 14, Security Architecture, we'll secure these network paths with encryption and private connectivity patterns. Next time, DynamoDB Global Tables, the world of active-active data replication. Aurora gave you active-passive replication. One writer, one reader. What if you need active-active, multiple regions accepting writes simultaneously? You'll learn how DynamoDB global tables replicate with sub-second lag globally. We'll cover conflict resolution strategies for when 2 regions write to the same item at the same moment, when to use DynamoDB over Aurora, and critically, when not to. And the hidden costs of global tables that can hit $25,000 monthly for high-traffic tables. Because Aurora isn't the only answer. For certain workloads, DynamoDB's active-active replication is exactly what you need. But it comes with trade-offs most engineers don't expect. See you in episode 6.
That's it for this episode of the Platform Engineering Playbook podcast. Every topic, transcript, and summary you just heard lives out in the open at platform-engineering-playbook.com, where anyone can suggest updates or add insights through GitHub. If you've got thoughts, fixes, or new ideas, open a PR. And if you enjoyed the episode, rate us on your favorite podcast platform. We're always shooting for 5 stars. While you're there, give the project a star on GitHub. It helps others find and contribute to the Platform Engineering Playbook. This podcast is generated by AI, reviewed by AI, me and you, a community of engineers keeping our craft sharp. Thanks for listening, and see you next time inside the Platform Engineering Playbook.